Okay, wanted to talk a little bit about calculation of momentum um, because we will come back to it later. So since we talked about particle in the box, we may as well use that as a workhorse for momentum calculations before we move on to the next topic. So I guess I would call it how to, calculating momentum from the wave function. There's a delay. So recall that if I give you a plane wave function, I think it's called plane, not like, 1 second. For a planar wave, for a plane wave function, if you measure momentum, you would always get h bar k. Okay? What if it's a superposition of two plane waves? With some complex code, let me use a big A. Okay? And then you would get either P1 equals h bar k1 with probability a square of the magnitude of A. That's not A squared. That's not absolute value of A. It's the square of the magnitude of A. Or you would get P2 with probability sorry, this is, yeah, this is A. This is so uncomfortable. Okay, so it's a superposition of two plane waves. Each one has a wave number, and so you can get either h bar k1 or h bar k2 with respectively with probability given by this or this. One step up, three plane waves, and so on. In general, the wave function is a superposition of infinite number of plane waves, where the weighting factors are given by A of k, the Fourier transform. Dk. And remember, omega is a function of k, omega of k. This is called the dispersion relation. For a free particle, omega is proportional to k squared. But in other situations, when it's interacting with something by means of potential energy, omega and k are related in some other way. But in general, this is this. Okay, so then probability. So now if you measure momentum, you would get h bar k with probability density given by the square of the amplitude of k. So for example, this thing can look something like this. This is k. This is probability of k. P of k, big probability, not momentum, probability. And it could be some kind of a thing. It does not have to be a bell-shaped curve. It does not have to be a Gaussian, right? But some kind of a curve. So this says that right here, this is the most likely value of momentum, but you could also get this or this. And remember, to convert k to momentum, we have to multiply by h bar. That's the relic of a de Broglie idea. So a of k, or the square of a of k, is the probability density for momentum. So now statistics. A mean momentum. So you repeat many measurements, then you can collect mean, standard deviation, k times probability of k, dk, as always, which is, sorry, this is not k squared, this is k. I don't know why this doesn't work. And if I wanted something like the mean of the square of the momentum, I would do this. Just a second, folks, sorry, let me. Okay. And if I want the mean of the square, not the square of the mean of the square. I would do this kind of calculation, and so on. These are difficult integrals. Most of you don't know how to compute these integrals. However, it turns out that, oh, by the way, so yeah, so this is the average k. To get the average momentum, you just multiply it by h bar. This is the average k squared. So to get the average momentum squared, you multiply it by h bar squared. So maybe I should just say this. No, I think this is fine. However, it turns out that we can compute e, p squared, etc. directly from the wave function. For example, it turns out that the mean momentum, which is h bar k times p, let me write it like this, times dk. It turns out that it equals to the following quantity. You take the complex conjugate of psi, it's a function of x, and you multiply it by the following thing. This is also a function of x. Why this equals this is not obvious at all. And I believe it's proven to you in Appendix E in your textbook, if anyone cares. It's a pretty hefty calculation. It's not obvious. But one can show that while you can calculate the momentum using the first expression, where A of k magnitude squared has the meaning of probability, it turns out that you can also extract it directly from the wave function using the following strange contraption. And similarly, the average of the square of the momentum is given by, I'm not going to write the fact that psi star depends on x. I will suppress mentioning the argument of the psi, but it's understood what this means. Minus I h bar quantity squared times the second derivative dx. And if for some strange reason you wanted this, you could compute times the third derivative dx, and so on. Okay. At this point, I'm just giving it to you, giving this strange idea to you. It's a very short class. There's no need to prove it. We don't have time for that. It's usually done in a real quantum mechanics course. But this is explained, I think, in your Appendix E of your textbook, why the first equals the second. Let's apply it to particle in the box. Since we've calculated the wave functions, okay? Okay, so for the infinite well, we already had a series of wave functions, a series of modal solutions. They're all pre-normalized for your convenience. Okay. So let's see, Pn average momentum. Let's just follow, I'm just going to apply this rule. Take the wave function, take its complex conjugate, and multiply by minus I h bar, and I multiply by the derivative of psi. Strange contraption, isn't it? And in this case, the limit is not minus infinity to infinity, but 0 to L, because outside of this bound, the psi is 0. So why would we integrate 0, right? It's just 0 to L. 2 over L, psi, and I'm suppressing the fact that it's a function of x. I omega mt minus I h bar times the derivative of uh, 2L psi m. And this is going to become plus, by the way, because it's a complex conjugate. Okay. So I had to squeeze this in, right? So this is, okay. What are these psi sub n? They're sine of knx. So first of all, notice the derivative acts on the spatial part. It doesn't act on the time. So I can write this as, well, first of all, root 2 over L times root 2 over L becomes 2 over L. Let me clean this up. Let me clean this up. It's 2 over L times minus I h bar. It's a constant. I can bring it out of the integral. Times 0 to L sine knx times the derivative, which is going to be kn times cosine knx times e to the I omega minus omega t. This is 0. This is 1. Sorry, this is 1. And the 0 is an exponent times dx. And I get minus 2I h bar over L kn can also go out here. And it turns out that this integral is always 0 because 2 sine of theta cosine of theta equals sine of 2 theta. So for any value of k, remember kn equals n pi. So basically I fit in integer number of waves. So there's as much of the positive lobe as the negative lobe or lobes. So average momentum equals 0. Does it make sense? Well, it makes sense because, well, so first of all, what does it mean the average momentum equals 0? It means if you have a bajillion particles in the boxes and you measure momentum on each one of them, some would be positive, some would be negative, and the average would be 0. So that's what this statistical result means. Does it make sense that it's physically 0? Well, we can kind of make sense of it classically. Remember, you have a bunch, or imagine you have a bunch of particles in the boxes and they're bouncing back and forth. Ping, 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 like a pinball, right? Particle in the box is just ping, 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 just bouncing back and forth. You close your eyes and you grab a particle. Some will move to the left, some will move to the right with the same speed. So on average, their average speed would be 0. So their average momentum would be 0. So that's kind of a classical way of making sense of this result. Okay, and then now I can compute, just for kicks, I can compute p squared bar between 0 and L. And then I have 2 over L times sine k and x e to the I omega n t. So that's the first thing times 2 over L minus I h bar squared. Let me write it like this. It's a pretty mathy calculation here, but actually not too bad. Kn times kn squared. There's a minus sign because I take 2 derivative, I get back the sign times e to the minus I omega n t dx. Again, these things cancel. If I clean it up, you get minus 2 over L h bar squared times minus k n squared and times the sine squared of k n x to 0 and L dx. This is always L over 2. So I get h bar kn squared, which is, if you put in the k, n pi h bar over L squared. and I can compute the standard deviation. This is 0, which is n pi h bar over L squared equals n pi h bar over L. Finally, I can check out the product versus n. I can calculate the product for first mode, for the second mode. The sigma x we computed last time. And this turns out to be kind of a fairly ugly expression. Nevertheless, whose units work out. N pi h bar times this thing, 1 over 12 minus 1 over 2 pi squared n squared. And what I can do is I can plot this versus the mode. I guess I should really call this sigma p, not sigma k, sorry. Because it's the momentum, the momentum that we're, averages of momentum that we calculate. The h bar is already figured in. So for n equals 1, okay, for this thing right here is 0.567 h bar, just a little bit above 0.5. So here's the Heisenberg limit, 1/2 h bar. And for the first mode, this gets closest to the Heisenberg limit, closest to the Heisenberg limit. So this is n equals 1. So here's 2, here's 3, here's 4. And so you would get something like 2, 3, 4. And very quickly, it kind of asymptotes to this line. The value doesn't really make sense for non-integer n. But it very quickly, you can kind of treat the n as if it was a non-integer, and you would get some kind of a curve that very quickly asymptotes to this straight line. And the straight line is n pi h bar over root 12. Okay? So that's the analysis. It's a fairly mathy discussion. I just wanted to present this idea to you right here, this sandwich of how to compute averages of momentum, momentum squared, and so on. And we will come back to it later. And so I wanted to show to you how that's done for completeness. And so that's how we can extract statistics of momentum from the wave function, and not just statistics of position. So the wave function contains a lot of statistical information. That's what I wanted to present to you. Okay, thanks. See you. Bye.